All right, everybody, welcome back. So now we're looking at cancer module number 2. So in this case, what we're going to look at is a case where we got 60 vehicle animals and we've got 60 treated animals. And the question that we're looking to answer is, well, this one right here. What is the probability that the treatment group developed tumors? That's the first big question. As you know, in the previous module, we looked at how do we figure out what the probability is in the vehicle animals with uncertainty. Now we want to know what is the probability with uncertainty for the treated group. And if we know that, then we can answer this next question, which is really at the heart of a risk assessment, which is the probability that the treatment group developed tumors greater than the control? And we are going to specifically only care about, in this case, greater than. And from a risk assessment standpoint, sometimes we will wonder if you see an increase of at least 1 in 10,000. And you could obviously ask the question I put in brackets there, which is, well, is that even a reasonable question? But let's not debate that right now. That's what we're going to look at. That's what we're going to do. So let's go back up here to the background. To refresh you, well, I should probably say I didn't change the data from the vehicle. So in the vehicle, we got 60 animals, and 5 of those vehicle-treated animals developed tumors. And therefore, if 5 developed tumors, then we've got 55 that did not, 60 minus 5, right? In treated, we also have 60 animals, okay? At the end of the bioassay, we have 20 vehicle animals that developed tumors. Whew, that's quite a few. If 20 developed tumors, that means that 40 did not. So this is going to be a pretty straightforward Bayesian type analysis. It builds off of what we did in the previous lesson. And so what we're going to do in this particular case is we are going to basically use the same stand code that we did before. Yes, okay. The only difference here, this part caught my eye, and that was, I had to remember, oh yeah, I did add that. So what we're doing is basically the same thing, right? The stand code has these blocks. The first block we write is the data block. In here, we've got the number of experiments and the number of successes, which morbidly in this case is the number of animals that develop tumors. We've got the parameter block. The parameter block is where we have the parameters that the model is going to fit and then spit back out at us. In this case, we are looking at theta. So theta is our probability of success. And then the reason why we're running this is ultimately to have this model, which then gives us the uncertainty bounds around that theta. And again, theta is going to be from a beta distribution. Again, we're using a flat uninformative prior for beta. If you don't remember what that is, go back and look at the previous lesson, and we talk all about that. It's really cool. And then here, we're using the binomial distribution. That is the actual model that we are using. Y is the number of successes, and so we're going to fit this binomial distribution to figure out what theta is that best matches Y. That's essentially how you read this line. Then you have these lines. This is new. We didn't have this before, and you might be wondering, what on earth is this? Generated quantities. So generated quantities is in STAN how we are going to get the posterior predictive distribution is what we call it. The posterior predictive distribution is the distribution when we feed in our best estimates of theta given the uncertainty. So it's going to take, if you remember, when we run STAN, we're going to get this distribution for theta. It's going to run this binomial random number generator. That's what the RNG means. For those of you who are not gamers, you probably don't recognize RNG. RNG is also gamer script for random number generator, and if you're playing a game that is heavily based on RNG, you might hear people complaining about the RNG, and that's what they're complaining about, is the random number generator. So this is the binomial random number generator. It takes the number of experiments, and then theta is going to be that probability of success. And in this case, we'll take the theta distribution that we calculate, and it will randomly draw the theta values that we have. So therefore, it will be our best estimate of theta plus the uncertainty to then yield a binomial distributed range of numbers. And then that information we can then use in order to validate this model here. So in other words, we're going to generate data here based on information from this model, and we're going to compare this generated data back to the number of successes that we had in the original data set, so the observed data. And if the observed data matches well the distribution that we get in y tilde, then we're going to say that the model is validated. And you'll see this in a little bit. So what I'm showing here is the stand file for the vehicle. It looks a lot like the vehicle from the previous lesson, except I just added the generated quantities. For the treated, it's the same. And the reason why it's the same is because we don't really have any new or better information to allow us to create a better prior. So we're still using this flat uninformative prior, beta 1,1. So this is identical to vehicle. I, as a best practice, like to keep my code separate for different models I'm going to build. So if I'm going to build 5 models, I'm going to have 5 stand files. They could all be completely the same, and that's fine. But for housekeeping purposes, I prefer to have one stand file per model I'm going to fit in general. So sometimes I do deviate from that rule just a tiny bit, but usually I don't like to deviate from it just from a mindset standpoint. Just keep myself in the mood and in the groove. So that is what I just mentioned there, is that new stuff about the generated quantities, and there's some more information about it. Like I said, this is going to be a pretty straightforward Bayesian analysis. Oh, this is some other stuff that I added in here that wasn't in the previous example. ggplot2 and HD interval. ggplot2 is a graphics library that is extremely popular right now because it's extremely easy to use. And it does a great job. I mean, the graphics are beautiful coming out of it. And then HD interval is the package or the library that we use in order to calculate the 95% highest density interval. Okay, so that's what those libraries are for. You should recognize RSTAN because we've been using it a few times. Here again, this is to make sure it's multi-core, and this is to make it so that the stand model doesn't have to keep getting recompiled every time if it doesn't change, because that actually takes a while. Here I'm setting the seed for R, and just so that you're aware, in Stan I'm setting the seed separately because Stan is actually running outside of the R environment. It's running in C, and so it needs to have its own seed specified if you want to get reproducible results. So let's go ahead and run this. And as you can probably tell, I've already ran this before. I've ran it several times because I don't like surprises. And what you'll see is, yep, there we go. Okay, so what we have is we've got our libraries loaded up. We've got our random seed set. Here's where we are compiling the stand model. And of course, like I said, I already compiled it before. This is nothing different from what you saw in the previous example. This is nothing different from the previous example. Neither is this. We run it, and then we get this right here. This is the output for vehicle fit, is this right here. So theta comes out to a mean of about 0.08. And if you remember, 5 over 60 is about 0.08, right? So, okay, that's pretty good. And the y tilde is what we're going to use in order to validate the model. So if you remember, if we go back to the description of what's going on here in the vehicle, we've got 5 vehicle animals that develop tumors out of 60. This y tilde is saying, okay, so given this information for theta, we are now going to estimate how many animals are actually coming out with tumors. And you can see that the mean is about 4.82. The median is about 4. And so the y tilde value, it's approximately 5. If you go by the median, it's 4. If you go by the mean, it's about 5. So we're going to say that, yeah, pretty much this model is, in fact, pretty well validated. And one thing that, we can do, change that up real quick, because it's so fast, it takes me no time at all. You can see probably, the theta here becomes 10%. It goes up a little bit. If we take away that -1 here and here, we do get the median. The median is at 5, and the mean is slightly higher. So anyway, that was just to show you what happens if you take that off and if you just change these numbers a little bit. So anyway, I'm pretty happy with what we have here with the -1. We explained that in the previous lesson, I believe. So the y tilde value is approximately 5. Everything's looking good. One of the things that's interesting, if you look at the 95% credible interval oops, I wanted to do it for, let's do it for this one. The 95% credible interval here, when I wrote this, I said stretched from 0 to 12 tumors. You can see in this particular case, because I didn't rerun it. Let me rerun it. It should come back. Yeah, it goes from 0 to 12. So that is 95% credible interval. What that means is that there's a 95% chance that, given the data that we have, for the population, the number of tumors is, going to be between 0 and 12. 95% likely. It's in that range. Now, also, 0 is not very likely because it's at the tail. 12 is also not very likely because it's at the tail. And you can see as you go in, it jumps pretty much, pretty quick. So anyway, gives you a median of 4. The mean's 4.82. So it validates pretty well. Let's do the treated group next. So we're going to run that. And it should run pretty quick. There we go. Again, here's our theta, 0.33. Now that theta is 0.33, so 33% is much different than 8%, right? 95% credible interval for the vehicle goes from 3% to 16%. For the treated, it's going from 22% to 45%. Okay, so just looking at it, you'd say, yeah, probably more than likely this treated group is very different from the vehicle, even with uncertainty. But before we get into that, we first need to validate the treated model. So we can see our y tilde has a mean of 19.35. We actually observed in the study 20 animals. That's pretty close. I'd say that the model's pretty well giving us what we'd expect. The uncertainty is certainly large, spanning from 10 to 30 animals for the 95% credible interval. And that's not really unexpected, again, because we are looking at only a single study. And that single study is kind of on the smaller size in terms of sample sizes at 60. So this is kind of what we would expect anyway. So the bottom line is both vehicle and treated models are validated. You can check that box. I'm checking it virtually into air as we speak. So now we get to compare the treated and the vehicle estimates to calculate what we would call an effect size. And so what we're going to use is the theta distribution. So we're going to use this information, and actually we're going to extract it from the model itself. Okay, so you can see here in this line here, we have the treated fit prob distro. Now remember, I like to remind you that you want to make sure that your objects have names that kind of make sense. And so when you look at this, especially if you work with me a lot, so anybody who's worked with me a lot knows that I don't like to write the word distribution because it's huge. And so in computer science and in coding in general, it's not uncommon for us to use some shortening of words, let's say. I'm also a fan of G.I. Joe. So therefore, there's a character there called Destro, and distro sounds like Destro. So, just kind of fun things for me. So I'm calling this object treated, which means it's treated instead of being vehicle. Fit prob is the fit probability from the model. And this is actually the distribution. So it's the probability, it's the fit from the model probability distribution. And the way you get this is you use the extract function that's in RStan. So extract, then you tell it what object you want. We want treated fit. And if you remember, here's treated fit. Treated fit is the name of the object coming out of the sampling function. And then specifically, I want theta. So I do $theta because I want this. I want our probability distribution, and that is held within $theta. Vehicle, same thing. So we're going to extract from vehicle fit, $theta. So I want to plot these as a histogram. And I'm going to use ggplot2 to do this, and specifically the ggplot function within ggplot2. In order to use ggplot, though, we need to use a data frame. So a data frame, the way I like to think of data frames is they're tables, all right? So in this case, I'm going to build a 2-column table. The first column is going to be called theta. The second column is going to be called group. Theta is going to have the treated fit prob distro values. So each one of those is an individual row. And then at the end of that column, I'm going to append on the vehicle fit prob distro. So if you were to look at this table as a whole, what you would see is you would see 2 columns, theta and group. The first X many rows are going to be the treated fit prob distro data. And then the next set of rows below that is going to be vehicle fit prob distro. And I know that's what's happening because I'm using C. C is kind of like the concatenation function. So it's going to concatenate one vector onto another vector. And that's what I'm doing. So I'm concatenating one vector onto another vector, and then I'm changing that vector. That vector becomes my column called theta. And I'm doing the same thing for group. So let me just run something real quick just so you can see it. So I'm going to run here. I'm going to run this one. I'm going to run this one. And what I want to do is I want you to see what treated fit prob distro looks like. It's a really long mess, but this is a vector. So the way to think of a vector is you've got a, well, the way I like to think of it anyway, is you have a really long table. And on this table, you have a series of blocks in a row going from left to right. The very first block is going to have this number on it. So I've got a series of wooden blocks. And the very first block in that series on the far left side has this number, 0.304197.3. Wouldn't that be fun if, when you got children, maybe babies are playing with these blocks instead of A's and B's and 1s and 2s and 3s or animal shapes, they have these huge decimal numbers. Wouldn't that be great? Well, that's kind of what you got here. So on the far left-hand side, you've got this one. The next one just to the right of it is 0.03013561. The one next to that is this one. The one next to that is this one, and so on and so forth. And you keep on going until you've reached like what would that be? 15,000 records. Okay, so now you've got these 15,000 blocks with decimal numbers on the face of them. And that is what a vector is. So that is what treated fit prob distro looks like. It is a vector of 15,000 wooden blocks that have these numbers on them. Guess what? Vehicle fit prob distro looks exactly the same. 15,000 wooden blocks. The far left one, though, has a different number on it. It has 0.09343949. The one just to the right of it is 0.09806,840. And then the one next to it is 0.12085130. Man, this is fun. I could just keep reading these numbers all day. But I'm not going to, because we got to get back to work. So that is how I envision a vector. Now, what's great about that vector is if you had really, really, really long arms, you could grab all 15,000 of those blocks, and then you could transition them, right, or transpose them, right, so that instead of being a row, they were a column. They were a column where the very, very, very first one, because we're starting off with the treated, is going to be 0.3041973. And you have 15,000 of those coming at you, right? So they start way, 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 way at the end of the table, and they're coming towards you. And then you have the other set of 15,000 blocks, which is the vehicle, and you put the first one of those at position 15,001, right? Because I have 15,000 of these treated fit prob distro blocks. That next one at the, so after the end of the treated fit prob distro at 15,000, 15,001 is going to be the first block for the vehicle vector, which is going to have a 0.09343949 on it. And then the next one after that in position 15,002, it's going to be 0.09806,840. And then in position 15,003, it's going to be 0.12085130. Isn't that beautiful? So you're going to have this huge column now of blocks, right? The next column next to it is going to be a label. And that label is either going to be treated or it's going to be vehicle. And that label is going to be based on the position, right? So I know I've got 15,000 of these treated fit prob distro blocks. But because I don't necessarily want to guess that that's what I have, I know that's what I have, but it's better to just tell the computer, you know what, use the length of this vector treated fit prob distro to repeat this label treated that many times. Okay, so let's read it this way. Rep means repeat. You're going to repeat this string called treated. You're going to repeat it for the length of the vector treated fit prob distro, which is 15,000. So therefore, it's going to make 15,000 strings called treated. And it's going to put those into, again, a vector. So I'm going to have 15,000 blocks with the word treated on them. So I've got 15,000 wooden blocks. The very first one on the far left says treated. The next one 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 says treated. I think you get the idea. And it keeps on saying treated until you get to block 15,000. Then at block 15,001, we're going to then, for the entire length of this vector, vehicle fit prob distro, which is again, how many? Say it with me. 15,000. All right, good job. 15,000 vehicles. So we're going to repeat this string vehicle 15,000 times, starting at position 15,001. So now I have my very first block that I have now engraved with the word vehicle. And I put that in position 15,001. And then position 15,002 says vehicle. Then position 15,003 says vehicle. And then position 16,000, so on and so forth until we get to the very, very end, which should be position 30,000. The last block says vehicle. All right. Now I'm going to take that humongous row and I'm going to transpose it so that now it fills in the column called group. So the group column is that humongous vector that says treated, 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 treated 15,000 times. And then it says vehicle, 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 vehicle 15,000 times, right? That's what it does. I'm going to run that line now. Okay. And now we're going to watch the magic happen. Let's make a plot. Oh, there we go. Look at that. That is so awesome. Woo. I'm so happy. Look at that. So this is your treated distribution. This, I don't know what color that is. Kind of greenish thing? I don't know. Somebody can email me and tell me what that color is called. I can't for the life of me remember. But this greenish, bluish weirdness is the vehicle distribution. And you can see, you know, this is our uncertainty, right? Our uncertainty is encapsulated in this distribution. And so you can see that there is a minor area of overlap here around 20%, right? It is in the tails for both of the distributions. So these are low probability events where they overlap. And over here is treated. So treated is clearly the mean or the median of treated is clearly out here past 30%. The mean or the median here is, you know, about 8%, right? So we can see, yeah, these aren't exactly overlapping distributions. They don't exactly look the same. They're probably not the same, right? So what we're going to do next is we're going to test this hypothesis. We're going to run this code. So again, I am, this is me being lazy is what this is. I already have treated fit prob distro, right? I already have it. I made it up here in 88. I already have this one too. I made it up there at 89. You know what I can do? I can just get rid of these. Just like that. Because I don't need them here. They're already in memory. And I can just run this line right here. This line is literally doing subtraction. I am subtracting the vehicle fit prob distro from the treated fit prob distro. All right. And I end up with this diff distro. So I'm literally taking this value and I'm subtracting this distribution from this distribution. Literally, that is what I'm doing. I'm going to form it into a data frame. Now in this case, I don't need that second column, that group column. I don't need that here because I just have one grouping, which is the difference distro. And again, because I'm being lazy, this is not a best practice. Please don't do this. This is just me being fast and lazy. I really should call this something more appropriate. I'm calling it Y. Not a great idea. If I saw this in code review, I would complain and I'd say you need to rename that to something that's more appropriate. So we're going to call it something more appropriate. We're going to call it diff distro. Okay. And actually, because we already called something else diff distro, we shouldn't call that. We should do it this way. DF diff distro. Just so that the computer doesn't get confused. And just so that the humans who read the code don't get confused. We get confused a lot. Okay, there you go. This, ladies and gentlemen, is the difference distro. Again, we literally subtracted this vehicle distribution from the treated distribution to end up with this distribution. If the two distributions were identical, the difference distro would be centered at 0. And you would see some spread. But it's not, they are not identical, right? We know that. We saw that. They are not identical. So we see that the most of the difference here is really around 25% or so if I had to eyeball this, right? Because this is 30%, this is 20%. So I'm just going to call this around 25%. Next, what we're going to do is we're going to use the 95% highest density interval and the region of practical equivalence as our decision rule. What in the world does that mean? Well, we talked about the highest density interval before, right? It is the region of the distribution that has the most amount of density in it. It is not necessarily the same as the credible interval. The region of practical equivalence is a region around zero difference that we are saying is, in biological cases, we would say that is biologically the same as no difference at all. So this region of practical equivalence, or we also call it a rope, R-O-P-E. This rope concept is how we bring biological information into the statistical inference that we're doing. So if you think way back to one of the first lessons, I was complaining about alanine aminotransferase. And I was talking about the fact that really we know as toxicologists that if your alanine aminotransferase levels are not like way up there, like 70s, 100s, something up, way up there, we know that that is no different than vehicle. So how do we calculate this rope? Well, we take that information, we say, where is vehicle? And now for a rope, I'm going to say that a difference that doesn't get me at least to 70 or maybe 100, 70 units is probably fair. A difference that doesn't get me to 70 units is still within the rope. That's how we set our rope. Got it? So for human health risk assessments, it is very common to set a de minimis risk rate, or de minimis risk rate of 1 in 10,000, which means that the probability in the treated group has more than a 1 in 10,000 increase over background risk. We consider that different from 0. That's just what most risk assessors use as a de minimis risk rate. So if you're less than that, they will not consider it to be an issue. Sometimes it's 1 in 1,000. It depends on the risk assessor. It depends on the rules. But for the US EPA, for cancers, it's not uncommon to use 1 in 10,000. And so now we will set our rope around that level, saying that the difference, we're not taking a point estimate of 0 and saying, well, if you're different from 0, then you're different. We're saying, no, 1 in 10,000 is really the limit. Well, 1 in 10,000 is going to be 0.0001. So if the difference is from 0 to 0.0001, that is our rope. Okay, if the highest density interval is within this range, then we are going to say there is no difference. If the highest density interval is completely to the right and is not included within the rope, then we will conclude that treated is different. That's how this works. If you remember, we do the HDI function, and we're going to feed it in diff distro. Remember, we create diff distro up here. We're going to feed that in, and here you go. That, ladies and gentlemen, is our 95% highest density interval. It goes from 11% to 38%. So in other words, 0 in values that are practically equivalent to 0, that is the de minimis risk of 0.0001, are not credible values based on the 95% highest density interval, and therefore we conclude that the treated probability is going to be different from vehicle. And the 95% highest density interval ranges from 11% to 38%. So there you have our uncertainty. We know that the real difference is likely somewhere in between 11% and 38%. So now we're going to calculate what this most likely difference is, and we're going to do such by using the median function on diff distro. So we again take diff distro, which, by the way, diff distro, if you think about it, is going to be a vector. Vector minus vector equals vector. So we are feeding into median this vector of distro, and it comes back at about 25%. So therefore, our conclusion is that the treated probability is different from vehicle, with a most likely effect size of 25% and a 95 highest density interval from 11 to 38%. Again, that 95% highest density interval is our uncertainty around our most likely value. Because our model's validated, we feel very confident that these numbers are real. And we feel very confident that we can draw this conclusion based on the models. But, there's a very large but. We are only looking at one study. We are only looking at one study of 60 animals. If we had more studies, if we had more animals, we would have much, much more confidence in our results. So, although I trust the models, I should say, I have a treated in a vehicle model, and the model's validated for this data, I feel pretty confident in being able to say, based on the information we have, and this is the key. This is the key. Do not forget this. Based on the current information that we have on hand, we believe that this treated group has an effect size of 25%, with uncertainty ranging from 11 to 38%. But we know that this is a single study, and we know that this is a fairly small sample size. The fact that this is a fairly small sample size gives me pause, because I would want to see this data replicated in an independent study before I feel sure that this is what we're seeing. I'd like to see it replicated in several studies before I felt really sure. Small sample sizes will tend to give us a little bit more, what's the right way to say this? We will tend to see these kinds of differences that are meaningful more often with small sample sizes. However, because we're using the Bayesian approach, small sample sizes are also going to give us more uncertainty. So I feel pretty confident that given, and it's not a small amount of uncertainty, we got quite a bit of uncertainty here. Even given that quite a bit of uncertainty, I'm pretty confident that yes, at this high dose, we probably are actually seeing a difference in tumor probabilities. So, it's one of those things. It's very hard for us to say definitively, but unfortunately, to paraphrase Donald Rumsfeld, we go into a risk assessment with the data we have, not the data we want. And so we have to deal with what we are given. Would I love to have 16,000 of these studies? I would love it. Ethically, is that problematic? Absolutely, that's problematic. We cannot do that. That's simply unethical. I'm not the biggest fan of animal studies to begin with. So, giving you all these animal-based examples is not exactly pleasant for me. But unfortunately, it's the data that we typically have. So that's why we're doing these. But again, the bigger question from a risk assessment standpoint then becomes, great, so we have this for rats or mice or whatever. I think in this case, I didn't say. But in my head, I was envisioning rats for this study. The real question for a risk assessor is, does this matter for humans? And I don't really have a good answer for that. I'm going to say maybe, maybe not. It's hard to say, right? Anyway, I'm going to get off my ethics soapbox with that, just to, again, reinforce the point that This is one study, doesn't have a lot of animals in it. I don't have a lot of faith in it. But based on the information that we have, this is what we've got. Anyway, there you go. That is lesson or part 2 of our cancer module. Up next will be part 3, where we do multiple doses. It's going to be fun. So I can't wait till you come back. All right. Thanks much.